You drill one well, you inject fluid into it. And depending on what the rock underground looks like, that fluid can travel completely different distances in completely different directions. This is the story of the single well tracer test, and why layering changes everything, whether you're chasing groundwater contamination or planning an oil reservoir waterflood. Picture a well that fully penetrates a confined aquifer, surrounded by concentric layers of rock. Each layer has its own hydraulic conductivity, a measure of how easily fluid moves through it. In this simulation, one layer is 10 times more permeable than the other. Inject fluid at the well, and it flows outward radially, symmetric in every direction, at least at first. Here's the well geometry used in the model: a fully penetrating injection well at the center, surrounded by n layers, each with its own thickness and conductivity, out to an outer boundary radius r. The flow itself is governed by the classic equation for steady, axially symmetric radial flow in a non-homogeneous, anisotropic aquifer, essentially Darcy's law written in radial and vertical coordinates. Once you add a tracer, its motion is governed by a second equation, the advection-dispersion equation, tracking how concentration changes as it's carried by the flow field and spread by hydrodynamic dispersion. Solve these together, layer by layer, and you can predict exactly where the tracer front will be at any moment. In the numerical experiment, the well radius is 1/4 of a meter, the aquifer is 20 meters thick, and it extends 200 meters out. 1,000 grams of tracer, represented by 5,000 particles, are released and tracked using a particle tracking random walk method. The high permeability layer moves fluid 10 times faster than the low permeability layer beside it. Watch what happens. Early on, the tracer front is already asymmetric, pushed further through the fast layer, lagging in the slow one. As time passes, 60 days, 600 days, thousands of days, the plume develops a distinctive stepped shape, hugging the boundary between the layers. Compare that to a version where the whole aquifer is treated as one average, homogeneous block. The plume there stays smooth and symmetric. It looks nothing like the real, layered case, and that's the point. The paper verifies this numerically against an exact analytical solution for the tracer front's mean position and its variance. The headline result: for radial flow, the front's average displacement grows with the square root of time, not linearly, like it would under a uniform gradient. And critically, simply averaging the conductivity arithmetically gets you the wrong answer. The right effective value, mathematically, is the average of the square root of hydraulic conductivity across the layers. Get that wrong, and your whole prediction shifts. This matters far beyond one paper. In groundwater hydrology, single well tracer tests are how we estimate hydraulic conductivity and dispersivity to track contaminant plumes and design remediation. In petroleum engineering, the same layered flow physics governs how injected water sweeps oil toward production wells. Get the layering wrong, and you leave oil bypassed in low permeability zones, or wastewater racing through high permeability streaks. Same governing equations, same lesson. Geology is never uniform, and treating it as if it were costs you accuracy in both fields. This simulation is based on Elfecki, 2003, published in the Journal of Hydraulic Research. If you work with aquifers or reservoirs, the layering isn't a detail, it's the whole story. Thanks for watching.